Hello, my name is Titus North. I'm the Executive Director here at Citizen Power, and today we are going to continue our series in our Energy Education Project workshops. Today's workshop is on photovoltaic solar power. Today we're going to be talking about solar photovoltaic, often referred to as PV, electricity. Electricity produced by solar cells. Now the main types of solar energy that are utilized are passive solar space heating, and this is through building design, building orientation, landscaping, location of trees, location of windows, or thermal mass collectors such as walls. Solar thermal, this is the next main type, and that includes solar water and space heating, solar pool heating, and concentrated thermal, where you're actually concentrating the heat of the sun onto a small area where you can boil water, produce steam, and therefore run a turbine to produce electricity. Those solar thermal technologies, including the passive space heating and the solar thermal, these are covered in another workshop that we will be doing later on in this series. But today we're concentrating on photovoltaic cells, the solar photovoltaic. So how do we make electricity? Most of the electricity that we make in the world is by electromagnetic induction, whereby a conductor moving through a magnetic field produces an electric current. So all we need to do is get something spinning. Typically, this is a dynamo. A dynamo machine consists of a stationary structure which provides a constant magnetic field, and then there's a set of rotating windings which turn within that field. This produces DC current. So you can have a dynamo or a turbine, which is very similar. The rotor is turned by moving air or moving water or moving steam. So if it's water, you can just harness a river. For air, we have the wind turbines that are becoming more and more common, and we talk about that in another of our workshops. But the most common way today is steam, and that steam is typically generated either through the burning of fossil fuels or through nuclear reactions. The fossil fuels come from the ground, so does the uranium ore. And here's a humorous little cartoon of two men. They're looking down, they're thinking old-fashioned. They're thinking of fossil fuels and nuclear ore, and they're saying there must be a source of energy down there. And of course, all the while, the main source of energy, the sun, is right above their heads. And in fact, fossil fuels are just a form of stored solar energy that was stored a couple of 100 million years ago, and now we're releasing it today. And that has consequences. It has consequences for our environment and for the climate. Now, photovoltaic electricity is nothing new. As a matter of fact, Einstein received his Nobel Prize not for the theory of relativity, but rather for explaining the photoelectric effect. And this is the process whereby electrons are stripped off of their orbits by photon. We'll be looking into that later in this talk. But the solar cell industry actually got started sometime in the 1950s, and as a matter of fact, there is a panel that the Japanese company Hitachi produced in 1960, and it's been in front of their offices in Japan, and it has been producing electricity every day for the past 53 years. And it is still working. It's only decreased slightly in its efficiency. So these things, they work. They've been around for a long time. And now that the price is coming down, they're becoming more and more common. What you're seeing here on this graph, there really wasn't too much photovoltaic electricity production going into the beginning of this century. It was pretty low, and it was mostly in America and Japan. What happened is as commodity prices started to rise in the middle of the last decade, with China and India and other developing nations requiring more and more fossil fuels, prices were rising, and with prices rising, it created more incentive to look to new alternative sources of energy. And so you see in the middle of the decade, especially in Europe, which is in orange down here, there was more and more investment and more production of solar photovoltaic electricity. And of course, in 2007, 2008, you started really getting a spike in the commodity prices for fossil fuels. Then, of course, in 2008, as you recall, there was a financial crisis, and many governments, in particular European governments, decided that the way they were going to stimulate their economies and get out of this financial crisis was through stimulus in particular in the energy sector, in the renewable energy sector. So there was massive investment in photovoltaic cells. And many companies around the world, not just European companies, but in China and in Japan, started investing really large scale into their facilities. And companies like Sanyo in Japan were doubling and tripling the size of their factories. And so you had this huge spike, huge increase in photovoltaic production. And you see this, and about 2/3 of it was in Europe. And here we're seeing Germany in particular was in the lead. And Germany, as a matter of fact, is moving completely away from nuclear power. They're going to shut down their entire nuclear power industry in the next decade or so, and replace it with renewable energies such as solar and wind. Italy is in second place, and so you're seeing other European countries, Spain, France, Czech Republic, and so Europe is making up just about 2/3 of the solar capacity in 2011. Japan is large. China is actually coming on very fast, and it's going to be a major producer. Well, Europe is investing in it. This is due to investment. It's not really due to their geographic location. As a matter of fact, most of Germany is pretty far north. Hamburg up here at 53 degrees is pretty much the same latitude as Ketchikan, Alaska. And even the southern cities in Germany, like Munich, is farther north than Montreal. Milan in Italy, the Italians being the second largest producers, Milan is almost the same as Montreal. And the Italian cities like Naples, they're still farther north than Pittsburgh, where our offices are located, here in downtown, beautiful, sunny Pittsburgh. Barcelona in Spain is farther north than Pittsburgh. Madrid is farther north than York, Pennsylvania. So these are not southern locations. So Europe is, even though it's in the northern latitudes, it's still able to produce electricity from the sun. Now here in the United States, we're seeing also an increase in photovoltaic installation. And again, you're seeing, after the 2008 crisis, you're seeing a big increase in utility-based photovoltaic production. You'll see a lot of this in New Jersey, for instance. If you're driving down the streets in a lot of places, you'll now see photovoltaic panels on telephone poles. So if you look by state, yes, of course, California, you would probably expect it to be the leader because of its sunny climate, relatively southern latitudes, and its large area. But here you see New Jersey second. And New Jersey, of course, is a very small state, and it's not particularly southern. yet it's able to produce quite a lot of electricity from the sun, more than Florida even. And then you see other states that you might expect, Nevada, Arizona, Colorado. But here in Pennsylvania, which I jokingly refer to as, sunny Pittsburgh, but Pennsylvania actually has Pittsburgh at least is probably next to Seattle is one of the most cloudy areas of the country. But photovoltaic technology will even work in a northern and relatively cloudy area. So you look here, this is insolation across the United States. Insolation, the amount of solar irradiance that is reaching the ground. And so it's no surprise that you see the most of it in the southwest desert. So you see a lot in California and Arizona, New Mexico, and Texas. And it's no surprise that you see relatively small amounts up here in the Pacific Northwest coast, and then also here around the Great Lakes in Pittsburgh. Yet we still have a fair amount of production here. And there is one other factor. If you're thinking of putting a solar panel on your roof, you're thinking not only of how efficiently does that panel produce electricity, but also what is the cost of the electricity that it's replacing. And of course, in California, the electricity can be very, very expensive. So for instance, down here in the southwest, in places like Arizona or New Mexico, which barely showed up on the graph on the previous frame, the electricity that it's replacing is mostly from coal-fired plants, which, although environmentally harmful, are very cheap to operate. Up here in the northeast, you're replacing much more expensive electricity. So the electricity in New England, some of that is produced even through diesel plants, which are very expensive to run. So you'll see that that even in the Northeast, because the prices of electricity are higher, that photovoltaics can be cost effective. Okay, here in Pennsylvania, you're seeing more and more rooftop installations. Here are some in the Philadelphia area, just on typical residential homes. You're also seeing some utility-based installations. This you can see from the Pennsylvania Turnpike. It's somewhere near Carlisle, and this is one way of producing a large amount of electricity. Now, one thing you have to consider, of course, is if you are using agricultural land for solar electricity production, you're competing with crop production. And so that's something that in some areas where the agricultural land is very productive, it might not be a good trade-off. But in other areas where there's, for instance, in Texas or in Nevada, where there's a lot of land that's not being used for agriculture or for grazing, that this might be a very good utilization of land. Here, the Carlisle Area School District, they have an array near one of their schools. Now, another thing to think about when you're deciding whether or not to install a solar panel on your roof are government programs aimed at encouraging solar installations. In Pennsylvania, and this is not unusual for states, in Pennsylvania they have an alternative energy portfolio standard. In some parts of the country, some states, they call it a renewable energy portfolio standard. And what this is a government mandate that utilities produce a certain amount of electricity from certain types of energy. So renewable energies would typically include wind, small-scale hydro, and solar, and geothermal. So in Pennsylvania, 18% of electricity consumption must be supplied by alternative energy by the year 2021, 8% from Tier 1, which is the genuine renewable sources, and 1/2 of 1% will be coming from solar photovoltaics. Now, in order to reach this target by 2021, you have this increasing requirement to go up gradually. And as a matter of fact, Pennsylvania has been exceeding these targets of recent years. Okay, let's look at the different technologies that are used. The most common technology is the standard crystalline technology. We'll be explaining this in just a second. There's a supercrystalline, also known as monocrystalline, which is based on one silicon crystal. There are some technologies, there's also the thin silicon technology. This is thin film technology. There are some technologies that do not use silicon. So this is cadmium tellurium. There's also copper iridium. These are technologies that don't use silicon, but the basic science behind it is the same. But today we're going to be looking at silicon, and in particular 3 different types of silicon technologies. So the thin film technology, this takes silicon and you spray it onto some substrate, which can be flexible, it can be a film. The silicon is not crystallized. This is the least efficient way of making a solar cell, but it's also the cheapest, and it can be useful in certain applications. The most common on the market today is polycrystalline. This is where molten silicon is poured into an ingot. Crystals form in a random pattern. The crystals are then sliced into wafers. The wafers are made into solar cells. The cells are arranged on a panel, and then the panels are arranged in arrays. And then there's monocrystalline. This is the most efficient in terms of its energy production, although it also has the most expensive production technology. In this case, a single seed crystal is put into a vat of molten silicon, and then carefully lowering the temperature and rotating the vat of molten silicon, the crystal is allowed to grow. So you get one large crystal, and it grows, and as it grows, the crystal is pulled out of the vat, and you wind up with these cylinder-shaped single crystals. This is the most, because it's one single crystal, it's the most efficient way of actually producing the electricity. Okay, polycrystalline silicon, on the other hand, is a much simpler production technology. You take molten silicon and you pour it into a mold, and you get these ingots. From the ingots, you can slice thin wafers, assemble them into cells, and then the cells are assembled into panels and into arrays. It's much cheaper, it's somewhat less efficient. The solar cells are arranged into panels, and then these panels or modules are arranged into arrays and put on top of a roof or out in a field. Now, monocrystalline versus multicrystalline or polycrystalline. If you're out on the street and you see a panel, you can often tell, even from a distance, which is which. There are 2 things that give the technologies away. One is for a multicrystalline, and I hope this shows up, you often see this kind of random pattern on the surface where the light is being reflected in slightly different ways, and it's a bit of random bluish tint that you'll see here and there, because the crystals formed at random, and they look different. The other difference is that with a monocrystalline panel, you will usually see these little diamonds between the cells. And the reason that there are diamonds between the cells is because the nature of the silicon crystal, as it's made through the process I explained earlier, it comes from a cylinder. You could cut the cylinders into wafers. You get round wafers, and you could cut those round wafers into squares, but it would involve a great deal of waste. You'd be wasting crystal that was very expensive to produce. Now the thing is, by doing this, you still have some wasted space in between the cells, and the overall module or panel efficiency on the monocrystalline is only maybe 1% or so superior to the polycrystalline. And because of the polycrystalline price advantage, the cost advantage in manufacturing it, this has captured more than 80% of the market. Alright, so where do we see these panels? You can see them on top of commercial buildings. You can see them on streetlights. You can see them in highways where it would be difficult to bring the electric grid out to the highway. They'll often have a panel mounted on an emergency telephone pole. You'll see them on top of carports, and this will be more and more common as electric cars become more common. Now, there was one other type of silicon solar cell that we haven't talked about. This is the amorphous silicon cell. It's the least efficient, and it's least efficient because it does not involve crystals. A thin layer of silicons is sprayed onto a substructure, which may be flexible, and this absorbs light very effectively. It doesn't produce electricity as effectively. The electricity is typically produced at around 6%, but it's very suitable in applications where flexibility would be needed. They can be made translucent, and you can make solar windows where the solar cells remove only a small portion of the light, transform it into electricity, the rest of the light gets into the room. Now here are some other applications. They have made solar cells into shingles, which can be integrated into a roof, and it's a very subtle way of installing solar on your roof. It doesn't attract a lot of attention. Here we have a solar installation using these shingles or roof tiles that were made with this amorphous silicon technology. It's producing a certain amount of electricity, which is equivalent to this solar panel over here using the more conventional solar cells. So you see, it doesn't produce as efficiently, but visually it blends into, at least on this side of the roof where the other tiles are blue, it blends into the neighboring tiles, and it's less noticeable. So this is showing your relative efficiencies, with monocrystalline at the top being the most efficient, polycrystalline in the middle, and amorphous on the bottom. Okay, let's just review a few key terms here. Insolation, that is the solar irradiance, the amount of solar radiation that's reaching the surface of the Earth in any given spot. We have equivalent hours of full sun. So if you were to have 1 hour of full sun, that might be equal to 2 hours of a cloudy sun, or 2 or 3 hours of sun late in the day when the sun is low. So this is just one unit for measuring how much sun you're getting at a particular location in a particular time. Photoelectric, this is what Einstein described. It is the excitation of electrons by light. Photovoltaic, this is using the photoelectric effect in order to produce an electric current, and we're going to be looking into that shortly. Voltage, this is a measure of electric force, the pressure of electrons in a circuit. So it's analogous to maybe water pressure. And Asian languages like Chinese and Japanese actually call it electric pressure. That's the words that they use. Amperage, this represents the amount of current being generated and distributed. It's the electric flow, if you were to use the water equivalent. How wide is the river, as opposed to how fast is it flowing. Wattage, This is the total amount of power developed in a circuit, and it is equal to the voltage times the amperage. So if you thought about the width of the river and the speed of the flow, that would be voltage times amperage. So it's, in that case, it would be the total amount of water molecules passing a given point in the river. Here it's the total amount of electrons passing a given point in the circuit. And then energy, which is power over a given period of time. So let's go back to our water analogy. If you were to have a water tank, and that tank is 10 meters high, there's going to be much higher water pressure down here than if that water tank was only 1 meter off the ground. And this is why you see water tanks that are elevated 100 feet off the ground, the municipal water tanks. That's why they're high, is to take advantage of the pressure. So this is analogous to voltage. Current, which is measured in amps, this is the water flow. And so you're going to get more water flowing if you have a wider diameter pipe than if you have a smaller diameter pipe. And as I said, power is voltage times current. Energy is power times time. Now, in this case, if you have water and it's high and you have the pipe coming down and it's just coming out, well, you just wind up with an empty water tank. But if you have gears or propellers, turbines inside, you can do work. That work creates resistance. The resistance equal load. The load is equal to work. And we can do this with electricity, just as you could spin something. If water is going through a pipe, you can do this with electricity. Now, how does photovoltaics work? Well, let's think about the atoms. So in your planetary version of an atom, you have, at the middle, you have a nucleus, and then orbiting the nucleus, you have electrons. Some materials are better conductors of electricity than others, and you'll find that your best conductors in their outer shell of electrons has maybe 1 or 2 electrons. Those will be most of your metals. They'll have 1 or 2 electrons, and they're the best conductors. The best insulators are those whose outer orbit, their valence shell, is almost full. So if they have 7 out of the 8 positions full, they are going to be insulators. And so the materials that we use as insulation, rubber coating, insulating a wire, for instance, you're going to find atoms whose outer valence orbit is almost full. Now in between we have semiconductors. So semiconductors typically would have about 3 or 4 or 5, but 4 is best, 4 electrons in their valence orbit. And so under certain conditions they're going to act more as an insulator, under certain conditions they're going to act more as a conductor. Here's your periodic table. So here we have, in this row, there's 1 electron in the outer orbit. When you get over to this row, it's headed by fluorine, you have 7 in your outer orbit. Here, of course, you have your noble gases with 8 in the outer orbit. The metals are mostly over here, and these are all 1 or 2 electrons in the outer orbit, and these are your best conductors. And this, right around in here, is where you're going to find 4 electrons in the outer orbit. Silicon is right here. Now, how do we take advantage of the photoelectric effect? Well, when electricity hits a photon, it gets excited, it jumps into a higher orbit, or it might jump out of orbit. It might jump out of the orbit of the nucleus, of the atom. It's going to jump up and then it'll fall back down somewhere. That in itself doesn't produce any electricity. What you want to do is get them to jump up from one atom and move in one direction, and if they're going to fall down, you want it to fall down in the same direction, and other electrons from behind to come and fill up that hole. So if they're going at random, if this electron jumps up and another electron's jumped up and they just take each other's places and they're going around in circle like musical chairs, that does nothing. But if you can get them to go all in the same direction, then you get a current. How do we do that? We do it through doping. Silicon has 4 electrons in its outer orbit. Boron, which was nearby on the periodic table, has 3 in the outer orbit. It's got 1 less electron. Phosphorus, which is next to silicon, has 5 in the outer orbit. What you can do is you can make kind of a sandwich. So with one layer you have your silicon crystal, but it's not quite pure. It has a little bit of boron here and there in the crystal structure. So the boron atoms are in the crystal structure, taking the place of silicon atoms. On your other layer of the sandwich, you have phosphorus doped into the sandwich, doped into the crystal. So a little bit of phosphorus. So on one layer you have every here and there you have a boron atom where there is an empty seat, an empty place in the orbit, an empty link in this crystal. So you have a hole in the crystal for the electron on that side of the sandwich. On the other side you have an extra electron. Okay, now let's look at how this solar cell works, this sandwich of semiconductors. It is a sandwich of positively and negatively charged silicon layers, with the N layer on the top having a little bit of phosphorus doped into the crystal structure, and the P layer on the bottom having a little bit of boron in that same crystal lattice. So the N layer is called N because it's negative. N stands for negative. The phosphorus has an extra electron. Now, this layer doesn't have a positive charge because the phosphorus has an extra proton as well, and likewise with the silicon. By connecting a load across the layers, this allows the surplus of free electrons a path to exit the top layer down into the bottom layer. This is the path that the electrons take. Okay. So now let's look at how the photovoltaic array ties into an electric grid. Okay. So we'll have the device, the solar cells here. There's a DC connect switch. And then they're tied to an inverter, which changes the DC power into AC power. A little bit of electricity is lost, but it's somewhere around 95% efficient. There is a disconnect switch between the inverter and your electricity meter, your house meter. The reason is that if electricity goes down in your neighborhood and the electric company is going to be working on the lines, they have to know that the electricity is down, and if you're feeding electricity into those lines, their workers could shock. So there's this disconnect switch which will prevent electricity from leaving your house and going into the lines when it shouldn't be, when the electricity is down. Okay, and here's your electric box, and then finally you have your electricity distribution meter and the electric lines. Your system would look something like this. So this is a little bit more than you're used to. I mean, you're used to having your electric box here. If you opened up this, you would have your various circuit breakers. But if you have a solar array on your roof, you're also going to have something like this in here that's going to take care of the other things. You're also going to have in addition to your regular meter, you're going to have something that is going to count how much electricity you feed into the grid. So your meter would measure that, and you get paid for that accordingly. All right, the photovoltaic key components. You have your module that actually produces the cell. You have your module that actually produces the electricity. There's an inverter that converts DC to AC. You have a controller that regulates the voltage from the photovoltaic panels to the batteries or to the load. You have batteries. Well, you may have batteries or you may not. If you're on an island in the middle of a lake in Canada, it's your fishing cabin, and there's no way that the grid's going to be coming out there, then you're going to want batteries. If you're in the middle of the city, you don't want batteries probably, because you can rely on the grid when your panel is not producing the electricity, and batteries tend to be expensive. Microinverters. Now this is a small inverter, so rather than having the entire array hooked up to one big inverter to switch from DC to AC electricity, here you have many microinverters. So on a cell-by-cell or panel-by-panel basis, actually I guess it's on a cell-by-cell basis, the electricity is being turned into AC. And the advantage with this is that if one of the cells gets knocked out or one of the panels gets knocked out, you still get electricity being produced by the others. What are the factors that impact your electricity production? Well, you have the module, the type of module, its specifications, its whether it's crystalline or polycrystalline or monocrystalline, whether it's got microinverters or regular inverters. Also, of course, the time of day. When the sun is high in the sky, you're going to get more production. The time of year, that when you're going to get longer days, obviously, in the spring and summer than in the autumn and fall. Your latitude is going to affect it. The farther north you are, the lower the sun will be in the sky. Your insolation, is there going to be a lot of cloud cover that is blocking sun from reaching your panel? The orientation of your panel, is it going to track the sun? Is it going to follow the sun? Or will it be stationary, always facing south, or is it facing away from south? Shading impacts. Do you have trees nearby? Okay, so here are some different types of mounts here. These ones are on the ground. These look like they're tracking the sun. These look like they're stationary. Here are some on a sloped roof. Here are some on a flat roof. On a flat roof, you might want to have your panels tilted so that they're going to catch the sun more directly. This is one way of measuring the tilt of your roof and whether or not you're going to want to mount it flat to the roof or try to have it on a rack that will keep it towards the sun. Okay, now remember how the path of the sun is going to impact your solar energy production. We think of the sun as rising in the east and setting in the west. That actually only happens 2 days out of the year. The rest of the time, if it's in the winter, it's rising in the southeast and setting in the southwest. And in the summer, it rises in the northeast and sets in the northwest. During the summer, the path of the sun through the sky is a much longer one. You get longer days. In the winter, you get the shorter days, the lower sun. And that makes a difference because you want your solar panel to be pointed towards the sun as much as possible. So should it be pointed higher in the sky, which will benefit you in the summer, or should it be pointed lower in the sky, which benefits you in the winter? Now, as it turns out, your best tilt is probably the happy median. This is for Philadelphia's latitude, which is just south of 40 degrees. And if you were to have the tilt at 60 degrees, you would be maximizing your production during the winter months. If you have it 15 degrees, only 15 degrees from the zenith, you're going to be maximizing during the summer months. If you have it at this happy median of 35 degrees, what you find is you're really only losing a little bit during the winter compared to the winter optimizing tilt, and you're only losing a little bit compared to the summer optimizing tilt. And so for the year as a whole, that is your best bet. Now, the roof orientation. Not every house and not every building has its front door facing due north or due south, due east, due west. And of course, in many areas, especially here on the East Coast, you have the slanted roofs. And this is the roof of the garage of Ron Celentano of Celentano Energy Services. He helped prepare these PowerPoints. And you can see that here's due south. His garage roof is tilted 55 degrees away from due south, 55 degrees away. We call that an azimuth of 125 degrees, which is 180 minus 55. Even so, he's really only losing a rather negligible amount of electricity. So you can be 45, 55 degrees tilted away from due south, and you're still going to be getting good production. This is an interesting piece of equipment. This is the Solar Pathfinder. It works kind of like a sundial. You can actually tell the time of the day and the time of the year from looking at this. But this is used by solar panel installers and also by landscapers. From this, looking down straight into it, you can tell where you're going to have shadows throughout the year and throughout the day, any time of day. So wherever you are seeing the reflection of these trees here, that's showing when that tree is going to cast a shadow. You're seeing these arced lines through here, and that would be the path. Any given one of these arced lines would be the path of the sun during that month. So in June, you're going to have this biggest, longest, curviest path right here, because that's when the summer solstice is. And you're going to see that these trees are going to be in the way in the morning, but then you're going to have several hours, most of the day will be unshaded. You can take a digital camera and analyze a digital photograph and analyze it that way, but there's an old-fashioned way. You can use a wax pencil, put it underneath the glass dome, and you could trace out this image here. And so this is a very nice analog, low-tech way of figuring out your overall insolation. Now there is another impact from weather, and this is kind of counterintuitive. When the temperature goes up, the photovoltaic effect actually becomes weaker, and you lose some voltage. Obviously, when you would think that with the more sunlight you get, the greater the current you get, and that's true. But this can be offset, because if the panels start to heat up, you lose voltage. And of course, power is volts times amps. Okay, here's a nice website you can go to, and you can plug in some information. You can find your latitude and your longitude. You can plug in your azimuth for the whatever roof that you're planning on putting something on, and this website will do the calculations for you, and you can tell how much insolation you're going to have at that location. So this is something you might want to do in the classroom. And you can add it up, and this can help you figure out how much electricity you're going to produce, and then given the electric rates in your area, you can figure out how much that's going to be worth, how much you might be able to sell back to the electric company, and also how many renewable energy credits that you're going to be producing. Now, of course, everyone wants to know how much this will cost. And it's hard to say, because the prices for various things go up and down. You do have a lot of upfront costs. So you have to pay for the model, and you pay more for a bigger one. What kind of accessories are you going to have? Are you going to have the microinverters? Are you going to mount it on a rack? That can cost extra. There's the labor costs. Now, there are also things that can offset this. The government may have tax incentives, tax credits that will help you. You might be able to get a grant that can offset some of these costs. The operating costs and benefits. Well, throughout the year, you're going to be generating electricity that you can use in your house, and that offsets electricity that otherwise you would have to buy from the utility. It does increase the value of your home. If you're going to resell your home and you have one of these on your roof, you're going to be recapturing some of your costs. Here is something that we'll talk about in just a second, the solar renewable energy credits. I'll explain them. There are financing arrangements. Sometimes you can have a solar panel put on your roof, and there may be an organization or an institution that will finance it, and they will purchase the electricity. They will pay for it, and then you may be paying them for electricity for a period of time until your unit has been paid off, and then after that everything is free for you. So, what the heck is a REC? A REC is a renewable energy credit, also called a renewable energy certificate. When your photovoltaic system produces electricity, it's generating two products. Okay. You have the electrons. That's the actual energy that you're producing, which you either consume on your own property or you can sell it back into the grid. But there's also this attribute. This is a requirement that many states have, that their utilities utilize renewable energy for a certain percentage of their electricity demand. What they do is any renewable energy producer, which could be a wind turbine operator, or it could be just a family with photovoltaic cells on their roof, they are allowed to issue these renewable energy certificates. They are credited with renewable energy credits for each megawatt hour of electricity that they produce. This is sold separately from the electricity. It's an extra amount of money, an extra payment that they can receive. It's in effect a way of utilizing the market to subsidize these forms of energy. Other forms of energy are getting different forms of subsidies. This is one way that the renewable energies technologies are getting a little bit of extra funds. There are markets for these renewable energy credits, and when the electricity providers, when they meet their requirements, they have to purchase these if they're not producing the electricity themselves. The prices vary. Here, prices could be from $30 to $75. That was as of January of 2012. They've been as high as $260. It's very difficult to say which direction they're going in, but they do have value. So, let's wrap it up. With solar energy, there's challenges, there's benefits. It is fairly expensive up front, but the costs are going down every year. They may not be applicable in all places. They require a large amount of surface space with sun. So if you don't have the right sun, if you have too much shade, they might not be right for you. The benefits, well, it's renewable energy. The sun is not going to be burning out anytime soon. We've got another 4 or 5 billion years that we can use it. It's clean. It's completely silent. It's safe. You can have battery backups in a remote location, or you can be hooked up to the grid in the cities. It's modular. There's very little maintenance. The technology is getting better every year. This is domestic energy, so you don't have to send the 7th Fleet out to protect the source of the energy. And it offsets your electricity bills for at least 25 years. And as I mentioned, there's There's a unit that's been producing electricity continuously in front of the Hitachi headquarters for over 50 years. So, let's go solar. I hope you enjoyed today's presentation. We have others that I hope you will check into and enjoy. And please let us know if you have any feedback. Thank you very much.